Good morning, afternoon, or evening, wherever you're joining us from in the world. Welcome to today's webinar. iPaaS is passé and hip ain't hip. What makes cloud-native integration different? My name is Alessandro Saini, Director of Marketing at Fiorano, and I'm thrilled to be joined today by Jason Bloomberg, Founder and Managing Director of Intellyx, and Atul Saini, Founder and CEO of Fiorano. Today, we will explore why cloud-native integration is the next evolutionary step past iPaaS and hybrid integration platforms, and why it is the best suited approach for tackling the unique challenges of today's business landscape. And without further ado, I'm going to hand it over to Jason.
Thanks, everybody, and thanks, Alex. Pleasure to be here. So let's get started. Here we are. So just a bit about Intellyx. We are a boutique industry analyst firm covering enterprise digital transformation, covering many different topics. So cloud native integration, one of many topics. And there's my Twitter and web address. Feel free to drop me a line or send me a tweet. So to get us started, let's place this discussion into its historical context. So integration has been around for many years, many decades, in fact. Started in the 1980s with message queuing. IBM setting up proprietary interactions between systems using message queuing technology. In the 1990s, enterprise application integration (EAI) became very promising set of technologies. It was still quite proprietary and on premises at that point, but it did solve a lot of integration problems that had heretofore had no solution. So it gave applications a way of interacting with each other. In the 2000s, we saw the rise of web services and then service-oriented architecture, and with it, a new generation of middleware called enterprise service buses, or ESBs, that leveraged XML and web services endpoints to provide a more abstracted integration, where it was no longer necessary to hard code integration endpoints, but rather you could use this common text-based language, XML, to facilitate integration. But it was still on-premises middleware, right? This was before the cloud hit. So as we move into the cloud era, REST became the dominant form of integration, representational state transfer, which was an HTTP-based approach. So basically leveraging the underlying protocols of the web itself to interact with endpoints as though they were websites and web pages, but leveraging the verbs of web-based interactions. And REST is still around with us today because it's very simple and straightforward, and it's proven to have quite a bit of longevity. And because it is internet-centric, it is no longer locked into the on-premises world that previous middleware approaches were limited by. So in the 2010s, cloud computing became more, dominated the scene, and all of the on-premises middleware approaches no longer met organizational needs. So it was time for a new technology, and integration platform as a service, or iPaaS, came to the fore, helping to leverage the cloud for integration, still leveraging REST as well for the most part, and moved the integration ball forward. And now we have, in the 2020s, we have cloud native computing, and we'll spend most of our time talking about what that is and how that fits into the story. So let's compare ESBs and REST to sort of lay the groundwork for this discussion of cloud-native integration. So ESBs, enterprise service buses, this was the on-premises middleware from the 2000s. I like to describe those as dumb endpoints and smart pipes. Right, the dumb endpoints were web services. Those are XML-based endpoints. Simply exchange text-based information with other endpoints, so it's very straightforward and not a lot of intelligence in the endpoints themselves. Instead, the ASBs provided all of the intelligence, the business logic, the routing, security was in the middleware, and this was fine as long as middleware met our needs. Now, REST switched this equation. Instead of dumb endpoints, smart pipes, now we have smart endpoints. Those are the RESTful endpoints leveraging the HTTP verbs like get and post. But we're relying upon whatever internet protocol we have, that, however the internet moves messages around. We're not relying upon any particular middleware. It could be any kind of middleware. It could be the internet itself. It could be any kind of networking technology under the covers, moves messages around. And now we're just leveraging this HTTP HTTP transport protocol to create the integration infrastructure we needed. So it solved a lot of problems, addressed a lot of the problems that the on-premises ESBs had, but still had this problem of dumb pipes, right? There was not a lot of intelligence in HTTP, and we were actually limited by some of the limitations of HTTP, because HTTP, being the protocol of the web, was never designed initially to create arbitrary application integration. So there were limitations as well that REST provided. So now along comes the cloud, and all of a sudden ESBs are now obsolete, and we needed integration as a service. So that gave rise to the integration platform as a service, where now organizations could leverage a third-party service provider to provide integration. So you would get your endpoints from the service provider, and the service provider in the cloud would handle moving the messages around. Hidden from view, it was just magic. Things just worked. And after that came the hybrid integration platforms, as hybrid challenges also became part of the story, where now organizations wanted to connect their on-premises technology to various cloud-based applications. So iPaaS did this as well, but it sort of led to sort of a fine-tuning of the category, where now hybrid integration platforms were essentially like iPaaS, although they could be technology that you would implement in your own organization, not necessarily in a public cloud, to connect on-premises technology with cloud-based applications. Okay, so this is the groundwork, the starting point for this discussion of cloud native. All of these, even though they're cloud-based and integrate with cloud-based applications, they're not cloud native, and we have to understand now what's the difference here. So what is cloud native? Well, essentially, we're leveraging cloud best practices. So all the lessons we learned in the cloud, horizontal scalability, abstracted software capabilities. We want to have dynamic software. We want to have rapidly scalable software. So we want to take those best practices of the cloud and apply them to enterprise infrastructure generally. So we want to be able to implement software dynamically, so we can have multiple teams updating software on a regular basis in a way that is rapidly scalable, the way we came to appreciate in the cloud. So much of the discussion of cloud native centers on Kubernetes, essentially the container orchestration platform that has now become the dominant cloud native infrastructure technology. But cloud native is more than just Kubernetes, and in fact, you can be cloud native without actually using Kubernetes. It's not required for the definition, because you can follow cloud native best practices using serverless technologies, containers that aren't running in Kubernetes. There's other ways to use containers that aren't part of the Kubernetes orchestration platform. And even traditional virtual machines, or VMs, can support this cloud native paradigm for enterprise infrastructure. So you can run in the cloud. Cloud native would suggest that it has to be cloud, but it doesn't have to be cloud. We're basically leveraging cloud best practices, but those could be on premises or on the edge, which is becoming now a dominant part of the cloud native story as well, or any hybrid combination of these. So now we have quite a bit of complexity where we could have more than one cloud. We might have different on-premises systems. We might be on the edge. We might have different parts of the edge that we want to integrate. And now we have a very complex enterprise scenario, which we refer to as hybrid IT or hybrid multi-cloud. So all of this now is part of the cloud native story. So there's many facets of cloud native. It's fundamentally a philosophy for building dynamic software at scale. Now, one of the things that people don't realize is that you don't have to follow cloud native best practices. If you don't require dynamic software, or you don't require hybrid or horizontal scalability, then cloud native may be more trouble than it's worth, right? There are many kinds of applications that simply are happy to live on premises or don't require a lot of scalability, and that's fine. You don't need to follow cloud native best practices. But if you want to have dynamic software and you want it to run at scale, then cloud native is really the only game in town. So the technology at its core, as I said, was Kubernetes, but it can leverage many different other kinds of technology. And now we have this story of cloud native infrastructure centering often on Kubernetes, but not necessarily, supporting cloud native applications. So there's just two sides of the cloud native story. There's the infrastructure, centered on Kubernetes, but not necessarily depending on it. And then we have cloud-native applications that leverage this infrastructure to support business needs. So more and more of the story is now about the applications that developers can build dynamically. So you can have multiple teams working on software at the same time and rolling out updates to software far more rapidly than we could in the 2000s or 2010s. And now it's becoming a core part of web scale companies and increasingly enterprises as well to be able to roll out software very quickly at scale in a software that is also dynamic, so it can deal with changes either in the underlying infrastructure, changes in the overall network or internet environment, or changes in requirements or a variety of different requirements across a distributed application landscape. So very complex kinds of scenarios, but the good news is we have infrastructure now that can support these type of complex requirements. So one of the challenges and why iPaaS and HIP are no longer up to the task of cloud native integration is the challenge of ephemerality. So ephemerality essentially means something that is designed not to last very long. So you see in the background, there's old postcards, and postcards are ephemera, right? They were never designed to last very long, right? People decided to collect them many years after they were mailed, and as a result, they are collectible because they are designed not to last. Well, in the context of technology, the challenge here is we have ephemeral pieces of software, microservices that can run in containers, but they may not last very long, right? Microservices might scale up, they might scale down, so you might have additional instances of microservices that pop into existence or disappear from existence very quickly. And you may be rolling out new versions of microservices on a regular basis, thus deprecating the older versions. So this is the core notion of ephemerality that is centered on the power of microservices, which is the core way of building software in a cloud-native environment. So microservices are generally stateless and ephemeral. So statelessness is an important part of the story, right? If you have some sort of application capability, you want to put it in a microservice, and you want it to scale horizontally, that means that your microservice, there might be one of them today, and there might be 100 of them tomorrow, all doing the same thing, and your traffic routes to different instances of the microservices depending upon your scalability requirements. Well, if each microservice had to keep track of information, it wouldn't scale properly because every microservice is supposed to do the same thing given a particular message that might be sent to that microservice. So that's the power of statelessness. So what this means is that if you want to maintain state, and of course applications are generally stateful, we have databases and application state information we need to maintain for the applications to work properly. We have to maintain state information external to the microservices. So a stateful microservice is actually a microservice that maintains state using the power of Kubernetes to do so in a way that it still retains the power of the ephemerality necessary to support horizontal scalability. So all of this presents a challenge to integration, because how do you connect to something that comes and goes at a moment's notice? This wasn't the way we thought about integration all the way up through the 2010s. We thought about integration as connecting A to B, where A and B were well defined, and we knew what they were, and we had endpoints that we could connect, and then integration was connecting them and getting the data to move from one to the other in a way that met our business needs. So what if A and B are no longer fixed, right? If they come and go on a moment's notice? Well, all of the traditional approaches to integration up to this point no longer work because of the ephemerality characteristic of microservices. And that's the fundamental challenge of ephemerality that leads to cloud native integration. So with cloud native integration, if you remember, ESBs were smart pipes, REST had smart endpoints. With cloud native integration, we want everything to be smart. So we need smart endpoints because we need to abstract the endpoints, right? A single microservice endpoint doesn't even necessarily have a fixed IP address because we might spawn multiple ones of them and they might have multiple IP addresses, or from one moment to the next, it might have different IP addresses. So we don't have any sort of fixed endpoint. We have to abstract the endpoint and have some sort of abstract representation of the microservice endpoint that we can resolve dynamically to the physical endpoint on the fly in order to move the messages to where we want them to go. So we also now need to have smart pipes. That is, the integration infrastructure has to be able to meet this ephemerality challenge. So we need to have dynamic scalability while providing the application integration that the business requires. So if you think about connecting A to B, where A could be one of many different things and B could be one of many different things, and those things are always changing, well, now this integration has to be done at an abstracted level in order to support business needs. So these sorts of changes happen on a moment's notice, and so we need this integration to be real-time and dynamic. So real-time behavior is a core part of the story as well, because we can't set it and forget it. We have to respond in real time to the changing needs of our infrastructure. But we also have real-time requirements as well that now we're able to meet with cloud-native integration. So this complex description of the types of applications we're able to support are essentially global in nature, hybrid. They include different clouds as well as on-premises or edge-based infrastructure, and inherently multi-cloud, where organizations want to connect 2 or more public clouds or private clouds in the mix. And we want to be able to integrate all of this stuff. So it's in order to create this kind of application. So this is where I coined the term global hybrid multi-cloud application. And for abbreviated GHMA, it doesn't mean that GHMA is a particular well-defined analyst category. Intellyx is too small to do that. And different people call it different things, where it's one or more of these component elements. But essentially, once we start describing what a global hybrid multi-cloud application is, then you'll see that this kind of description describes many enterprise applications that organizations either have or want to build. So what are the 5 core principles? Well, global infrastructure, right? If you're starting to think about hybrid multi-cloud, you're not thinking about any particular physical location. You may have different physical locations which could be around the world. So now you have to think about global concerns like data sovereignty, right? Different regulatory constraints having to do with where you put your data. Latency is always an issue, right? If we're moving messages around the world, we have to follow the speed of light. There's just no way around the speed of light. Messages take a certain amount of time to get to where they're going. So if we have a global application, we have to deal with latency on a regular, ongoing basis. And then we have to deal with user experience, right? It's not just the infrastructure that may be located around the world. Users are located around the world as well. Many times we're building applications that support users in different jurisdictions, leveraging different internet technologies with different performance characteristics. They may be using landlines, they may be using or fixed LANs, fixed networks, or more often than not, they're using their phones, which now have different protocols to connect to things as well. And so all of that has to be supported with this integration paradigm as well. So hybrid technology, it's not just hybrid infrastructure where we have on-premises and different clouds, but we also have the technologies are different in different places, right? On-premises technology often is legacy technology of various sorts. Maybe you still have web services that are sending out messages. Maybe you have other kinds of endpoints. Mainframes are a core part of the story as well, and mainframes are every bit as important as they were 50 years ago, if not more important. And so they're a core part of this hybrid story as well. So of course, we have cloud-based technologies as well as edge-based technologies, which may or may not be in the cloud. They may be in a teleco point of presence. They may be in a gateway in a server room somewhere, or they may be at the physical endpoint, with a device or a Internet of Things endpoint, actuator or a sensor in your factory floor or in a truck or in your automobile. So all of that is part of this hybrid technology story. Multi-cloud is clearly a part of the story, right? We have multiple cloud environments across geographies, both public and private. And these days, private cloud is really any kind of modern enterprise infrastructure, because we're leveraging cloud best practices, whether we're in a co-location facility or in an enterprise data center. All of these are now becoming private clouds in one sense or another. So all of this is part of the multi-cloud story. So now real-time behavior is a key part of this as well, because we now need to have real-time behavior from connecting any endpoints around the world, where we no longer want to stop and wait for something to happen, right? The infrastructure has to support real-time behavior. We want to We want to have a user experience where we have very rapid response times, regardless of the complexity of the underlying infrastructure. And we want to have real-time messaging behavior that moves messages in real time. So that could be for streaming, for video or audio, or it could just be very high performance message traffic that we don't want to follow a request reply pattern any longer, where we don't want to wait around to request information from a database and wait to get the result. That's too slow for us these days. We want to move much more quickly, especially since we need to move messages around the world. So this whole notion of GHMA is fundamentally distributed, right? So we have to follow core distributed architecture best practices, right? No single points of failure, and we want to be able to roll with the changes, right? Distributed infrastructure has to be inherently resilient because parts of it may fall off the network or may respond slowly or may have other technical issues, and we need to be able to work around those in order to provide the application experience we're looking for. So all the lessons you learned about distributed infrastructure apply, if anything, even more so with this kind of application. So why are the iPaaS and HIP, the hybrid integration platforms, not good enough for GHMAs? Well, they were never designed to deal with global concerns, right? Because they had this earlier generation integration paradigm of connecting one thing to another. That's not how global applications work. Global applications have many different endpoints scattered around the world and that are inherently dynamic. So traditional integration approaches like iPaaS and HIP just aren't up to the task. iPaaS and HIP, even though resilience is built into these, it's not like we're saying that they're not resilient. So, they do respond to issues on with the underlying infrastructure. They're still insufficiently resilient to deal with these complex combination of distributed components. There's just no way you can rely upon iPaaS or HIP if your endpoints are scattered all over the world, coming and going all the time with dynamic, perhaps flaky network connecting them. And of course, if we have real-time behavior, we want it to scale. And scaling real-time interactions is a very hard problem because we have all of these issues of ephemerality as well as the latency issues that just make real-time behavior very difficult to get right. We want to make sure that the end user watching a video feed is getting the experience they need, even though the underlying infrastructure is extraordinarily dynamic and diverse and globally distributed. It's just a very hard problem to solve. So Kubernetes alone isn't good enough either, right? Kubernetes is a part of the story, but it's not solved the whole problem because Kubernetes is essentially designed to work within a single environment, right? You might have Kubernetes in the cloud or you might have it on premises, but you have your Kubernetes environment. And in order to get Kubernetes to work in different environments, you have to have some sort of cloud-based integration or cloud-native integration connecting those different Kubernetes deployments. And Kubernetes alone doesn't do that for you. So if you talk to the cloud providers, each cloud provider has their own Kubernetes as a service offering, and they'll provide integration within their clouds, and they'll provide integration with particular hybrid integration scenarios, right? Integrating AWS with something on-prem, for example, or Azure with something on-prem, or perhaps between two different clouds, but not globally distributed, right? The cloud providers, they're not in the business of helping you create these globally distributed hybrid multi-cloud applications. So what this means is we need additional cloud-native integration capabilities beyond what Kubernetes alone gives you, beyond iPaaS or HIP or any of the earlier generation of integration technologies. So that's my setup for Fiorano. So hopefully you sort of realize that all of these challenges that I've described is Fiorano is well suited to address. So I'll turn it over to Atul now. Atul, take it away.
Hello, everybody. I'm Atul Saini. I'm the president of Fiorano. So I'm going to talk about how Fiorano fits into the cloud-native integration story here. Well, Fiorano has an architecture for the last 20 years, which hasn't changed. So we've always been cloud-native before the cloud was around. I know this sounds a bit strange, but it's a fact. So the concept is like this. The way the architecture of the system works, it's a peer-to-peer distributed architecture, right? it's a peer-to-peer architecture, which means you have runtime peer servers, which could be anywhere globally. Oh, this keeps moving, sorry. It could be anywhere. So you could have peer servers in the Amazon cloud, in the Google cloud, Azure cloud, on-premise, literally as many as you want. The peer servers are connected to a centralized controller, which is the place where you sort of compose your microservice flows. So the way the system works is you have a centralized controller and you drag, drop, and connect microservices and connect them up with directional lines. So you essentially create a graph where the endpoints of the graph represent the microservices, and the lines between the microservices map at runtime to real-time event flows. So now the question becomes, how do you map this to a global hybrid infrastructure, right? How do you do that? The way that says, the way that happens is quite interesting. Once the graph is constructed, when you decide to deploy it, the microservices are actually moved just like agents from the centralized location. For instance, you got one here, and you could have the Google cloud could be in America, the Amazon cloud could be somewhere in Europe, and the Azure cloud could be in the Middle East or in Africa, or really anywhere you want. And you can dynamically deploy the microservices onto any of the peers that are in the clouds. And you suppose you have microservice 1 in the Google cloud that wants to send a message to microservice 7 in the Amazon cloud across different continents. The system does all of these connections for you automatically. Well, as Jason had explained, the microservice is stateless. That means it gets data, processes the data, and puts it on the output ports. So it doesn't know where the data is going, and it doesn't have any centralized state store. This is a very important point. Jason had mentioned, for instance, scaling integrations is extremely difficult at a global level. And the reason is that if all of the state of the system is maintained in a centralized controller, like that becomes very difficult. The system simply won't scale. So in the Fiorano platform, the centralized controller is just an administrative connection. Data does not flow through the centralized controller. Data flows peer-to-peer, directly between the microservices. And if the microservices are on different clouds, the Fiorano system automatically ensures that the message flows from microservice A to microservice B in a different cloud in an optimal way using peer-to-peer connections. So the infrastructure itself is it's global. You could have peer servers anywhere in the world. It's hybrid in the sense that some of the peers could be on cloud, some could be within the enterprise. It's multi-cloud. As you can see from the diagram, the peers can be in any cloud, and the microservices are auto-deployed from the central controller onto the cloud, and all the details of the different cloud platforms are abstracted away. So as far as the end user is concerned, as far as you're concerned, you're simply composing this microservice flow, clicking a button, and it's all getting deployed globally, and the system works out of the box. So you don't have to do any middleware programming, et cetera, et cetera, et cetera. So the architecture is distributed, and most importantly, the routing of the information, the routing of the messages is handled within the message. So the state of the system is also maintained within the messages. There's no centralized data store. So you could have 500 microservices distributed across 20 different peers on 5 locations worldwide, and all of the messages are flowing in parallel. So if you have a graph or multiple graphs, the disconnected components of the graph can all operate in parallel, right? So and message flows, there's no request reply concept in the system. You see, you can always build request reply over an event-driven platform, but you can't build event-driven technology using message flows on top of a request reply platform. This is just a theorem in computing, right? So you have these connections, you create and compose the flows, And the flows, once deployed, can be extended dynamically at runtime. So for instance, if I got a flow that says A arrow B, that means microservice 1, once it produces a message, sends it to microservice 2. Very simple. And microservice 1 could be in New York, the microservice 2 could be in Dubai. I can simply at runtime, add microservice 3 and add an arrow from Dubai to London. And the system will work out of the box. The microservice gets added on the fly, and you can take the first microservice off the flow. So it has the ephemerality, it has the dynamic scalability, the architecture is distributed, on the fly changes, and it works across multiple cloud platforms. I mean, the average enterprise today is using about 2.8 clouds. The large enterprises and the mid-sized enterprises are using about 2 clouds besides using the enterprise. So you need to have infrastructure that can scale across multiple clouds, across geographical locations, and of course, work in a hybrid environment as well. So this is a lot of information to digest. It just sort of so quickly, but you take my word for it. It's literally a microservice is a piece of software with inputs and outputs, which carries its own dependencies. So if you have a database of microservices, let's say in one location, at the click of a button, you can actually move the entire microservice off to a peer server sitting in one cloud. And once it's there, you can create all these flows dynamically at runtime. So the support for GHMA is the infrastructure is global. You can be deployed from a single location, let's say in Nairobi, and you can be running on peer servers in New York and Dubai. It runs on all major platforms. All you need is a JVM. So you can run, once you have a JVM, you can deploy on top of the JVM. You can be on a mainframe, you could be on a Linux system, it could be Java, really Windows or any operating system. And besides all the various key clouds, you also support on-premise. So you really have a global hybrid sort of platform infrastructure. And it's multi-cloud, as we've already said. You can run as many clouds as you want. They could be in different locations. You just have to the only initial setup you need is you need to install the peer servers in all the clouds. You need to decide where you want to keep your controller. The controller could be, the management and repository server, where you compose your flows and click a button, and you can also monitor everything. So only the administrative information is sent back from the peer servers to the centralized controller. So the system scales. The data flow is peer-to-peer. The administrative control is centralized. So you get the benefits of centralized control of classical systems, and you get the benefits of peer-to-peer technology. Now, obviously, when you have this connection between microservice 1 and microservice 2, you're really creating real-time messaging between the two. They're high-speed, standards-based messaging using JMS technology. So you've got standardized messaging going at hundreds of thousands of messages a second. It really depends on your hardware across the internet. So the entire system is real-time. So and because the biggest killer of performance is centralized state management. So if you have a Kubernetes system or any other system, if you have a standardized system that it's got centralized state, every time a microservice wants to send a message, it's got to write the state. That doesn't work. This is what most systems today have some kind of centralized control and centralized state management, which kills them. Unless the state is carried within the message, and this is something very few people have actually figured out, the system can't scale. So literally, if any system wants to scale as well as us, they've got to literally build exactly what we've built, and we really haven't come across it till now, right? So it's not location dependent. The peers can be anywhere on the globe. You can make flow changes dynamically at runtime using just drag, drop, and synchronize. And it scales in real time because the messages carry the entire state of the system, and you have ultimate parallelism. So if if your flow diagram has A to B, C to D, E to F, those are 3 parallel flows, and they map to fully parallel systems at runtime as long as you got enough pair servers, right? So the system is distributed. There's no single point of failure. So if you have, for instance, as messages are flowing, you'll have multiple pairs. And if one pair is down, you route it to a different pair for processing, right? The message contains the state of the system, so it scales very, very easily. And we have both horizontal and vertical scaling. So for instance, in the diagram over here on the right side, in the middle diagram, if you've got MS1, MS2, MS3, 3 microservices, microservice 2 is slowing you down. You can start additional instances of microservice 2 on the same machine, right? And what that would do is it would speed up the whole throughput. If microservice 2 is the bottleneck and messages are queuing up before this in this queue over here after MS1, then you can take more items off the queue by starting additional instances until, of course, you saturate the CPU. Oh, sorry. Right? And then you can have vertical scaling. Vertical means you can start additional instances of the microservice 2 on a different pair server, and the data is routed automatically to the proper instance for additional scaling, right? These are all implemented within the system. You can get any level of scalability. Of course, the system literally is as easy to operate as I make it out to be, but it is still a Formula One car, so you really need to know what you're doing, and this is a very important point. But essentially, there's no programming in the system. Once you've created the microservice, everything is visual, and you draw lines between microservices which dynamically map to. It's essentially like doing all your middleware programming, and the system is doing it for you. So we've got the GHMA concept fully implemented. In fact, Fiorano, along with Intellyx, has coined the term global. It's hybrid. It's a multi-cloud, and it's distributed and real time. So that's how we support it. And you can, if you need a demo or something, that's something you can contact us whatever through the website or by other means. I think at this point we can hand it over to the Q&A team. Thank you.
All right, thank you. Everybody feel free to type your questions into the Q&A section. The box is right there at the bottom. We have one question right now, and the question is, what if I am not using any public clouds, but I have multiple data centers spread across different locations? Can I still use the principles you've outlined here? So over to either Atul or Jason.
Jason, you want to take that question, or should I? Go ahead.
Well, it really doesn't matter, right, where you put these peer servers, as long as they can reach the internet, right? As long as you have connectivity, then they'll behave as they should behave, whether they're in a cloud or on premises. So, exactly. I mean, it's this isn't designed to be an air gap network. It's designed to be global, which means that it is taking advantage of the internet or other wide area network connections. But it's really neutral with regards to how you're actually providing the network connectivity. As long as it's there, this will run.
Absolutely. So if you have private data centers, there's no problem at all. It's not like it has to be a cloud. Absolutely not. It's just literally any point to any point. And we use the cloud metaphor because it is just a very important thing for a lot of people. It seems to be very difficult today when you talk about multi-cloud because everyone's doing everything manually. There's no platform that is already cloud native, which brings us to the point that Jason made right through his talk, that the cloud native means you have a platform that abstracts away all the details of the various clouds on the enterprise. So once you got the peer servers installed, and connected to the repository server, it doesn't matter. The peer service could be in private data centers, and you're all set to go.
So, Atul, I have a question for you. What
Sure.
happens if one of these peer servers fails, or falls off the network somehow, right? It loses connectivity. Then what happens to your application?
There's a high availability and active mechanism, and there's absolutely no message loss. So anything that was sent there, the last message is rerouted to the standby peer server, and it's processed as before.
And then your controller as well. What happens if it fails?
The controller runs in high availability mode, and that all automatically fails over to the HA instance, which is more of a classical setup. And that's something that's it's a very rare happen. The controller usually doesn't have too much load because data is not flowing through the controller.
So another question. How does Fiorano support auto-scaling, and how does it work for a hybrid platform? To add to it, how do we address scaling concerns for real-time integrations involving legacy backend systems?
Yeah, so to answer your question, the last slide of my presentation showed you the horizontal scaling and the vertical scaling. Talking about legacy systems, right? Well, you have to have a microservice connected to your system, and scaling in a horizontal, for example, vertically means on the same machine, you have a flow, microservice 1 connected to 2, connected to 3. So let's suppose the middle microservice 2 is slow. Scaling vertically will mean that you start multiple instances of this microservice, right? And you route the data automatically to all the instances. So if the middle microservice was slow, when data comes, it will get backed up on the message queue before the service, but you'll have 5 instances or 10 instances of the service depending on your scalability requirements, and you'll be processing them as fast as possible. So that's how you scale vertically. So in the context of a legacy system, it's the same thing. You'll have a microservice connected to the legacy system. Start 5 instances of it. So if data is coming in very quickly into the microservice, and the microservice cannot process it all very fast, and this microservice is connected to your legacy system. So any message that comes in, the legacy system processes it, brings it back, right? So the way it will work is you have multiple instances, and they all sort of operate in parallel, talking to your legacy system. That's how it would work, essentially. And if that was too quick an explanation, what we can do is you can just contact us, and we can go through a session and show you the whole thing, show the entire thing working, and with actual examples showing, it is 5 messages per second. You're producing messages, 50 messages a second. The second step is 5 messages per second, which is connected to a legacy system. And then the downstream step can process 100 messages per second. So you got to speed up this step. You start multiple instances, and you can see the whole thing working. Good. Next, another question.
Yeah. Another question. Which of the cloud infrastructure providers, GCP, Azure, AWS, AliCloud, etc., is Fiorano tested to be stable and working across all of these?
The 3 we've tested on extensively on AWS, on the Google Cloud, and on Azure. So those 3 are fully tested. If there are other cloud, these are the sort of popular ones. On-premise, extensive testing, obviously. And so there's really never been any issue. If there's any other cloud system in particular that you may be using, you just let us know about it. It's a very straightforward process it's really a question of just installing the peer service there. So it's not a very complex port from our standpoint.
Okay. There is one question that I found relevant pertaining to the scalability, which is when you're referring to multiple instances of microservices to scale up, would it be limited by the specs of the machine, which the hardware that it's deployed in?
Yes, of course. Exactly. So the whole concept of vertical scalability is your CPU utilization. You can just add only as many instances of the microservice as your CPU can support. If that doesn't work, you just have multiple pairs. Let's say you got 2 more pair servers on different machines, and then the messages will auto-direct to those pair servers which will have an instance of this microservice. So you have the horizontal scalability to help you out. That's the benefit of a peer-to-peer architecture with event flows. None of this can work in a request-reply environment because each microservice is independent of the other. And once a message leaves one microservice, it doesn't know where it's going. The system routes it, right? So if the message is routed to a different peer server, 2 different peer servers, you're going to get that scalability. But of course, it is absolutely limited by the CPU utilization. So the autocontroller that we have takes into account the CPU utilization, and you can set limits based on the CPU utilization. And usually we find the CPU is not the limiting factor. The message queue fill up between the microservices is. So that's something you have to test. Again, performance is really not something that, in theory, you can say a lot of things, but in practice, it's all about, what happens in real time on your machine. So the system is straightforward and easy to use and very easy to describe in terms of concepts, but how you configure the queues, the configuration limits, these things make a big difference, as we know from a lot of experience in a lot of enterprises, put it that way, without revealing more.
All right, we still got time for a few more. So here's another good one. One second. So we've got there's some great ones from the audience too. So we have a global telco customer looking at building an enterprise middleware layer to cater to their unprecedented seasonal demand and volume surge, which can go 800% up for a couple of months. Do you think Fiorano might be a right fit here?
Jason, why don't you take a shot at that?
Well, I mean, I should let you speak to how well Fiorano can do this, but the whole point of having the distributed peer-to-peer architecture is that simply by adding peers, you can address any scalability requirements that you need. And adding peers is straightforward, right? It's just a matter of standing them up. So you clearly have to plan ahead, say, well, what kind of infrastructure do we need to put in place? But there's nothing about the Fiorano architecture that limits the number of peers, right?
Exactly. So you can really have, if you have 800% load coming up, you can plan ahead before the season, have a bunch of peers, they can be deployed dynamically. You can have them on standby, and you can have your flows built up and your HA architect and your scalability architecture. You can do some testing beforehand and make sure it's all ready to handle the load. And it's a very simple system. So even, if you find the load is increased beyond your testing capability, you can dynamically add more peers and make the system work. So I would say yes. The whole system is designed exactly for this sort of situation, especially in telcos. Telcos is a prime example. The load just takes off, and it's very up and down. Is that sort of thing.
Great. And we have some more verticals here. My core banking platform is on Azure. Is it better to provision Fiorano on my Azure instance or use the SaaS instance of Fiorano?
It's probably better to place the Fiorano server on the Azure instance, because you see, if you have it in the SaaS instance, that communication time between the SaaS and the Azure, it can be a lot more than you think. In theory, everything travels at the speed of light, but in practice, with integration, it doesn't work. We can tell you from real experience, you have to have it in close proximity. Very important. So it's best to have the peer server in Azure. Your controller, your administrative and repository server can be anywhere. You can have multiple peer servers in different private data centers, and you can get all the communication you want. You can do the core banking integrations. You can do real-time integrations with Swift and with various legacy systems. It's all possible. So we would say, yes, please install it in the Azure instance.
Yeah, just because you can put peers anywhere doesn't mean you should put peers anywhere.
Yeah.
What it means is you should put peers that optimizes your latency figures, right?
Exactly.
Latency is something that you can't eliminate, right? It's just a reality of the way that modern networks are set up, and the speed of light limitation. So when you think about, well, okay, where should I put my peer servers? You're going to put them in places that give you optimal latency characteristics, whether it's a high performance for your end users, or in this situation, you want to have a high performance between a core banking app and the peer servers. Yeah, put the peer server near the core banking app. That makes a lot of sense, right? So you can put them anywhere you want, so put them in the best places.
Right. I mean, the network infrastructure person, hardware infrastructure person will tell you, oh, this is super fast. You can put it anywhere you want. Put this in Kenya, they put the other stuff in London. It doesn't work like that. It's better to put it next door. So there you go.
Jason, I know you got some questions too. Do you want to share?
Yeah, well, we're running out of time, but this is one question I had for Atul.
Got one question about.
Yeah, and I know, Atul, I saw Kubernetes on one of your slides, and I made the point that Kubernetes isn't necessary for cloud native, but it is a part of the Fiorano infrastructure, right? So what is the role of Kubernetes? Is it in the peer server or what?
You can deploy peer servers dynamically using the Kubernetes system. You have a peer server with a whole set of cached microservices. You can deploy them dynamically. So, for example, in the telco instance, right, if you needed to deploy peer servers dynamically, you would use the Kubernetes instance of Fiorano and use the Kubernetes system to control how many you want to deploy and how many you want to spin down, spinning up and spinning down. So that's one area where Kubernetes fits in. There are others, but we'll stop at that for now. Thank you, everybody. Thanks, Jason.
Thanks, everybody.